Hi everyone, so we are going to be looking at factors that affect the rate of reaction. Last time we looked at the collision theory, which mentioned that for a reaction to happen, particles must collide. They must collide with proper orientation and with the activation energy. Particles need to have the activation energy. And any factor that's going to increase any of these is going to increase the rate of the reaction. So these factors include pressure, concentration, surface area, temperature, and catalyst. So when you increase the pressure, you will increase the rate of a reaction because high pressure means more collision of particles. So if you can visualize it like this, actually pressure and concentration have the same impact. So it can be visualized like this. So when you have high pressure, there's more collisions and there's going to be a faster reaction. Same thing, low pressure means lower rate of reaction. Now, when we talk about liquids and solids, then pressure will not affect these. Pressure only affects gases, rate of reaction of gases, because liquids and solids are incompressible. If we're talking about liquids, then concentration will affect the rate of reaction. An increase in concentration, as you can see here, means there's going to be more particles per unit volume, which means that you're going to increase the number of collisions and you increase the number of successful collisions. A decrease in concentration, you have less collisions. Surface area, this concerns solids. When you have smaller solids, smaller size of the solid, so when a solid is broken down into smaller pieces, as you can see, there's more surface for collision to happen. So smaller pieces means that it has a large surface area. So smaller pieces, surface area increases, rate of reaction increases. You may consider this relationship where surface area is inversely proportional to particle size. So small particle size, large surface area, and large surface area means large rate of reaction. So rate and surface are directly related, but both of these are inversely related to particle size. So over here you have a big particle, so particle size is big here in this example, but surface area is small, and if surface area is small, then rate of reaction is less. So here you have lower rate, here you have higher rate. Then the other factor is temperature. When temperature increases, it increases the average speed and kinetic energy of all the particles. So kinetic energy of all the particles increase, therefore the average speed of the particles increases. When the speed of the particles increase, they move faster, they collide with one another more often. When the average kinetic energy of particles increase, it also increases the proportion of particles with sufficient energy. So if you remember the graph from last time, you can see here that when temperature increases, so T2 was higher temperature, when temperature increases, you have the number of reacting particles increases because the number of particles with energy greater or equal to activation energy increase. This is what is meant when it says that there is a greater number of particles that have sufficient kinetic energy for the reaction to happen. So there's greater number of particles with energy greater or equal to activation energy. Let's see this question now. So you're given the graph that shows volume of oxygen gas being produced in this reaction here. So then the volume of gas is being used to relate to rate of reaction. So this is going to be used as a measure of rate. Now sketch and label 3 curves in the figure for all of these. So pause the video, try it out, and then check your answer. Now let's see what happens when concentration of hydrogen peroxide increases. Hydrogen peroxide is our reactant. If you have more reactant, you're going to get more product. So then the volume of gas will be higher. So then the graph will end around here. It will be higher. But because you have higher concentration, and concentration is one of the factors that affect rate, higher concentration means higher speed of reaction, higher rate of reaction. This means that the gradient, the initial gradient of the graph is going to be steeper. So this is for part 1. Then the second one, lower temperature. Lower the temperature, you are not going to change the amount of product that you get. The amount of product stays the same. You will only reduce the rate because rate is directly proportional to temperature. Right, so lower temperature, rate lowered, but you get the same amount of product. So the graph will join the initial graph. So this will be number 2. Now if we look at the third one, when you increase atmospheric pressure, here we're looking at volume and here we're looking at pressure. So I have the relationship, pressure is inversely proportional to volume. So when pressure increases, volume decreases. Now if you look at this reaction, you can see that this is aqueous and liquid. So aqueous and liquid means that they are both liquids. Therefore, pressure will have no effect on the rate of reaction because here oxygen is the product. It's not part of the reactant. So the pressure will not affect the rate. So initial rate will stay the same, but then the volume is going to be less. So your graph should initially start, but then you're going to have less product. This will be graph 3. Let us now see catalysts. Now, catalysts will increase the rate of a reaction, but they will not be consumed in that reaction. So a catalyst is itself not used up, and it will only provide an alternative pathway. So if you can see here in blue, if this was the initial pathway of the reaction, the new pathway is in red. So it is an alternative pathway with a lower activation energy. Now, if we look at this graph here, at this energy profile diagram, you will see the transition state. So the transition state, if you still remember, it is a very unstable state and it cannot be isolated. And in this state, you have bonds being broken and bonds. In this transition state, you have bonds being formed and bonds being broken at the same time. When you have a catalyst, it will provide intermediate. This is where the intermediate is here. And an intermediate, it could be isolated. It is more stable than the transition state. There are 2 transition states here. The peaks are the transition states, but the more important thing about catalysts is that they produce an intermediate. The intermediate can exist in the reaction mixture for a certain period of time. So the important thing that you have to know is that a catalyst increases the rate of reaction by providing an alternative pathway with a lower activation energy. And if you remember, activation energy is always from level of reactants to the peak, to the transition state here. And for the uncatalyzed reaction, same thing, from reactant level to transition state. Now, whether you have a catalyst or you do not have a catalyst, the overall enthalpy for the reaction stays the same. So enthalpy is always from reactants to products. In this case, it's like this, delta H. So whether it is without catalyst or with catalyst, delta H stays the same. Without catalyst, activation energy is here. So from reactants to peak, or if you want, you can draw it like this. So from reactants to peak, this is activation energy without, and with catalyst, if you can write it like this, here this is activation energy with catalyst. So over here, now you're going to sketch a labeled energy profile diagram for an endothermic reaction showing a catalyzed and an uncatalyzed reaction. What you have here is delta H going down, so delta H is negative. So if delta H is negative, it is exothermic. Now I'm going to be looking for delta H being positive in an endothermic reaction. So pause the video, try to work it out, and then check your answer. So this is the graph. Things that you have to pay attention is the axes that have to be labeled. This is reaction progress, this is energy. And you can see here you have delta H positive. So this is an endothermic reaction. And here in green you have the profile of an activated, of a catalyzed reaction. So this is activation energy of catalyzed, and in pink you have activation energy of uncatalyzed. It always goes from level of reactants to the peak. And do not forget to label here reactants, and on the other side products. If you have specific reactions given to you, you will write the chemical formula or the name of that specific chemical as reactants and products. Now, the effect of a catalyst can also be explained using the Maxwell-Boltzmann distribution curve that we did last time. So here is the curve, and if you look here, if there's no catalyst, this is the activation energy, but with catalyst you can see that there is a reduction in activation energy. So the curve stays the same, it's only the activation energy that is shifting. A lower activation energy means that more particles, so this area here, if I can draw that in pink, this is the area, this is the number of particles that have sufficient energy to react with each other. So rate of reaction increases. Now, both temperature and catalyst will affect rate of reaction by altering proportion of particles having kinetic energy greater than activation energy. This means that temperature and catalyst will affect number of particles in this region. A rise in temperature will not affect activation energy, but it will increase the average kinetic energy of the particles in general. A catalyst will not affect the average kinetic energy, but it will reduce activation energy. So both of them will have the same effect, but one, temperature impacts average kinetic energy, catalyst impacts activation energy. In both cases, the frequency of successful collisions increases, therefore rate of reaction increases. Now do this question, pause the video, and then you check your answer. Because it's increasing rate of reaction, therefore this is acting as a catalyst. Now if you look at NO is produced here as a product, and then it is again used up. So it is produced momentarily. Therefore, this is going to be N, intermediate. And you can see that there is only one intermediate here. If you look at the answer, nitrogen 4-oxide increases rate of reaction. It's written here and is regenerated at the end, as you can see here. And NO, as you can see, it's produced at the end and reused. So it is produced at the end. So it is an intermediate. So it is formed and reoxidized in the second step. Now, your graph, you need to have your axes ready, energy and reaction progress. So this will be for the uncatalyzed reaction, where here you have delta H is less than 0. So delta H will stay the same whether it's catalyzed or uncatalyzed. You can see that I have labeled specifically the reactants and the product using the overall reaction. Delta H is less than 0, so I've included it here. And I'm going to also include activation energy, which is from level of reactants to the intermediate. This is activation energy without catalyst. Now, with catalyst, you can see that NO is the intermediate, like this. Therefore, over here, I'm going to have NO. This will be where NO is going to be found, and the activation energy is going to be from this to here. So this is activation energy of catalyzed.